Hello, all. So welcome to the next session on theory of scattering. So today we are going to find the explicit form of the Green's function that we have stopped in the last session. So in the last session, what we have found is the total wave function psi of r can take the form psi instead of r plus 2 mu by h bar square integral the Green's function g of r prime v of r prime the psi of r prime dq bar prime. So this entire term can be treated as a scattering wave function. The scattering wave function would take the form 2 mu by h bar square integral the Green's function v r prime psi r prime dq bar prime. Okay, now the technique that we are going to use to find the expression for the Green's function is by with the help of the Fourier transformation. Okay, so if you just recall the definition for the Fourier transformation, suppose you have a function f of r, you can convert this function f of r to some other basis q. Okay, maybe as we can call it the reciprocal basis. So f of r can be converted to f of q, or better we can put f tilde of q. So the f tilde of q is called the Fourier transform of the function f of r, which is defined as f tilde of q is integral e raised to minus I q dot r f of r dq bar. Okay, so this way you can convert your the function which is based on r, the real basis, into a reciprocal basis q. So this transformation is called Fourier transformation, and its inverse is also possible. This we can find f of r from f tilde. So f of r can be written as 1 by 2 pi cube integral. Okay, better I can write exponential term first, e raised to plus I q dot r f tilde of q and integrating over d cube q. Okay, so this is called the inverse Fourier transformation. So it is always possible to change our variable, okay, from the original basis to a reciprocal basis and vice versa. Okay, if you look at q, the dimension of q would be the inverse of the dimension of r. So this is your r. So dimension of q would be the inverse of dimension of r. So that is why the q space we can call as a reciprocal space. Anyhow, in certain cases, this the treatment with the reciprocal space will help us to find the solution, or the mathematical steps similar. Okay, so it is always used in max, such kind of transformation, the Fourier transformation, Laplace transformation, or logarithmic transformation, and so on. Okay, so for the time being, we'll deal with the Fourier transformation. We'll convert our Green's function into in the Fourier form, Fourier transformation. Okay, so the Green's function, which is a function of r and r prime, can be converted into a reciprocal space g tilde of q. Okay, so how will you define this g tilde? So g of r comma r prime, which that would depending upon g of modulus of r minus r prime, because the Green's function has a translation invariant. So the Green's function g of modulus of r minus r prime, I can write it as 1 by 2 pi cube integral e raised to I q dot r minus r prime g tilde of q d cube q. So this the definition of the inverse Fourier transformation. That is, you can find the g tilde of q, or you can find the Green's function from g tilde of q. Okay, so it is okay for you, I think. So what is the opposite step? And that is how to define the Fourier transformation of the Green's function. It is simply e raised to integral e raised to minus I q dot r minus r prime and g of r minus r prime d cube r. That's it. Okay, so this Fourier transformation and is the inverse Fourier transformation. And another thing we can recall is the definition for Dirac delta function. So a Dirac delta function, which is d delta q of r minus r prime, this can be written as 1 by 2 pi cube integral e raised to I q dot r minus r prime d cube q. So this is the integral representation of Dirac delta function. There are many representation for Dirac delta. So this is one of the representation. This you might have studied in your mathematical physics. Okay, it's an integral representation of Dirac delta function. Okay, now if you look at this expression and this expression, you can substitute these two in our the original differential equation, which defines the Green's function, which is del square plus k square acting on g of r prime Dirac delta function r minus r prime. So the above two expressions, these are the, this look like the inverse Fourier transformation. So these two inverse Fourier transformations definition can be substituted here. Okay, so then what will you get? Del square. Okay, better I will write in the next page. So del square plus k square, and the Green's function is 1 by 2 pi cube integral exponential I q dot r minus r prime g tilde of q d cube q equal 1 by 2 pi cube integral e raised to I q dot r minus r prime d cube q. Okay, so I've just substituted the Green's function and the expression for the Dirac delta function. Now this del square acting on r. Okay, so del square is depending based on r, not on r prime. So del square can act here, and we'll get iq square outside, so that will give minus q square. Okay, so this expression would become 1 by 2 pi cube integral minus q square plus k square exponential of I q dot r minus r prime g tilde of q d cube q equal 1 by 2 pi cube exponential e raised to I q dot r minus r prime d cube q. Okay, now just comparing from on this left side and right side, we can identify that this term must be equal to 1. That is minus q square plus k square multiplied by the Fourier transform of the Green's function must be equal to 1, or the Fourier transform of the Green's function g tilde of q must be 1 upon minus q square plus k square. So it's very easily we have found the expression for the Fourier transform of the Green's function. Now, since we got the expression for the Fourier transform of the Green's function, we can find the original expression for the Green's function by just integrating it. Okay, so what was that expression? It is the Green's function, which is g of r comma r prime, or g of r minus r prime. That would be equal to 1 upon 2 pi cube integral exponential of I q dot r minus r prime, and g tilde of q would be 1 upon minus q square plus k square into d cube q. Now, how to integrate this expression? Okay, so in order to integrate this expression, we can use the spherical coordinate system. So we can have a spherical coordinate system. So this the Green's function g of r minus r prime can be written as 1 by 2 pi cube integral I q dot r minus r prime. Okay, let us define the angle between q and r minus r prime as theta. So this become I times mod q modulus of r minus r prime, the cosine of angle theta, divided by minus q square plus k square, and d cube q will take the form q square sine theta dq d theta d phi. Okay, so that's the usual the spherical coordinate system that we are using, and there are triple integration. So integral over phi would go from 0 to 2 pi. Integral over theta will go from 0 to pi, and integral over q would be from 0 to infinity. Okay, so this become 1 by 2 pi cube integral 0 to infinity e raised to. Okay, before going to that, first we have to integrate our theta. So that will be 1 upon dq q square dq divided by minus q square plus k square integral 0 to pi e raised to iq modulus of r minus r prime cos theta d theta, then integral 0 to 2 pi d phi. Okay, so this integral will become 2 pi. There is no issue. And what about this integration? Okay, in order to do this integration, first better you can have a substitution. That is, this cos theta we can convert, and you can put as x. So x is cos theta. So dx will become minus sine theta d theta. Okay, so the d theta would be 1 upon minus sine theta. Okay, and okay, sorry, I forgot to write a sine theta over here. So this become 1 by 2 pi cube, and there is a 2 pi over here. This integration becomes 2 pi. So this become 1 by 4 pi square integral 0 to infinity q square dq upon minus q square plus k square, and this integration 0 to pi. When theta becomes 0, x become 1. When theta become pi, the x become minus 1. Okay, so 1 to minus 1 plus 1 to minus 1 e raised to iq mod r minus r prime x sin theta d theta will become minus dx. Okay, so the integration is simple. You can integrate it, and if you integrate this minus sign can be converted, minus sign can be used to flip the integration limit, and the integration of the exponential function is very simple. So this become 1 upon 4 pi square integral 0 to infinity q square dq divided by minus q square plus k square, and this become integral minus 1 to plus 1 e raised to iq modulus of r minus r prime x dx. So 1 upon 4 pi square equals 0 to infinity q square dq minus q square plus k square. This become e raised to iq modulus of r minus r prime times x divided by iq modulus of r minus r prime, and the limit is from minus 1 to plus 1. Okay, so then we will get two integrations. So 1 upon 4 pi square integral 0 to infinity. If you put x equal to 1, this become e raised to iq modulus of r minus r prime into q square divided by minus q square plus k square into dq times, okay, one q would cancel, one q will cancel, and there is an I here. Then it is modulus of r minus r prime, then minus 1 upon 4 pi square integral 0 to infinity e raised to iq modulus of r minus r prime. So this become minus e raised to minus iq modulus of r minus r prime q dq divided by I times minus q square plus k square modulus of r minus r prime. Okay, so far so good. There is no issue here. So I have just put the limit plus 1 and minus 1. So plus 1 upper limit and minus 1 lower limit. So the upper limit minus the lower limit, and we'll get to integration. Now it is possible to change our the second equation. So the second equation, the second term, which is integrating over dq. Now in second equation, I can convert q to minus q. If you convert q to minus q, this q become minus q and dq become minus dq. That minus minus will cancel, and this minus will become plus, and there is no change for q square, because if you change q to minus q, the q square and minus q square will be the same. So what would happen if you convert q to minus q to the second term? Okay, so better I will write in that in the next page. Put q to minus q to second term. If you are putting q2 minus q in the second term, what will you get? 1 upon 4 pi square 0 to infinity e raised to iq modulus of r minus r prime divided by I minus q square plus k square modulus of r minus r prime q dq minus 1 by 4 pi square. And if you make q2 minus q equal to 0 would become minus q is also 0, and q equal to infinity become minus q become minus infinity. So therefore the limit would be 0 to minus infinity, and here it become exponential of, instead of minus iq it become plus iq modulus of r minus r prime minus q minus dq, that would be same as q into dq divided by I times minus q square plus k square modulus of r minus r prime. Okay, so there is a minus sign in the integration from 0 to minus infinity. So this minus can be converted into plus. Then the limit can be interchanged. The limit can be written as from minus infinity to 0. Okay, now if you look at these two expressions, the second term is integrating from minus infinity to 0, and first term is from 0 to infinity. So therefore, what is the final result? So the final result would be 1 upon 4 pi square, and you can take some terms outside. 1 upon I modulus of r minus r prime can be taken outside because you are integrating over q only. Then integral from minus infinity to plus infinity e raised to iq modulus of r minus r prime divided by minus q square plus k square q dq, and this is your the Green's function g of r minus r prime. So now we have got the expression for the Green's function, and now it is not the final result, because what we need is we have to do this integration. Okay, now how to perform this integration? So the performing this integration is not very straightforward. We have to use the complex analysis technique to do that. Okay, because that integration comes with the exponential e raised to I. So better we can have the complex integration, because if you, in this instance, integration is going from minus infinity to plus infinity and integration over dq. So at some point minus q square may become minus q square, the q may be equal to plus q. So at some point the denominator may become 0. So there is a singularity in this integration. Okay, there exists a singularity. So there exists a singularity at which all points? So singularity or poles at q equal to plus k, and as well as q equal to minus k. Okay, so since so if this becomes 0, then it will go to infinity. The integrand go to infinity, then the direct integration would be impossible. the final result would become infinity. So there are ways to find the integration of such problems using complex technique. So we have to convert this integration from real plane to a complex plane, then we can integrate. So we can see how to do that. So you have to consider a complex plane. So there will be a real Q and as well as a complex Q, imaginary Q. So real Q and imaginary Q. Real part of Q and imaginary part of Q. So actually this integration is from minus infinity to plus infinity. But in between there are poles. Okay, at some point there would be Q equal to minus K, and at some point there would be Q equal to plus K. So these are the 2 poles. So how to integrate it? So the better way of integration is we can start from minus infinity. Then you have to exclude some of these residues and include this one. Then make this a complex integration. Okay. So what you have to do is you have to integrate. So instead of integrating over the real line, we'll integrate over the complex plane, and that would be closed contour. Okay, so we have to integrate over a closed contour. So if you are integrating a complex integration f of z dz over the closed loop, then it would be equal to 2 pi I times of sum of residues. 2 pi I times of sum of residues. And how to find residue? Residue you can find at poles. So suppose if z0 is the pole, then residue can be found from z minus z0 with f of z0. Okay, so this is the complex integration technique, and you might be aware about this. So we are using the this result in order to find our the integration, because our integration, if you look at the Green's function, so g of r comma r prime, which is 1 upon power pi square I times of modulus of r minus r prime integral minus infinity plus infinity e raised to iq modulus of r minus r prime minus q square plus q square times q dq. So your function is this. This entire term is a function, and it has the pole at q equal to plus k and at q equal to minus k. So first we can find the residue at q equal to plus k first. Okay, so the first residue. So first residue I am denoting as r1. So r1 can be known as q. So z instead of z is the variable is q here. So q minus k. So what I am going to find is residue at q equal to plus k. Then the function is the entire function f of k. Okay, so instead of q you just put k. Then what would be the result? Q minus k e raised to ik modulus of r minus r prime divided by minus q plus k then q plus k into k. So this q minus k and minus q plus k would cancel, and there can be a minus sign. So the and you have to put q equal to k. So this become a raised to ik modulus of r minus r prime divided by minus k divided by 2k. So this k cancels. So final expression will be minus e raised to ik modulus of r minus r prime divided by 2. So that is the residue at when q equal to plus k. So similarly, we can find the residue at q equal to minus k. For the time being, better put r2, and that can be done by yourself. There is no issue for you. So what would be the result if you find the residue at r2 q equal to minus k? What would be the result? Just guess it. It become q minus k become q plus k e raised to minus ik modulus of r minus r prime divided by minus q plus k and q plus k. There is a q here, and we have to put q equal to minus k. So this q plus k cancels, and if you put q equal to minus k, so that will become 2k and k here. So this become e raised to minus ik modulus of r minus r prime divided by 2. Okay, so only difference, there is no minus sign over here. So then we can find the corresponding Green's function. So the Green's function corresponding to the residue at q equal to plus k. Green's function, which is g of r comma r prime. This can be split into g plus r comma r prime plus g minus r comma r prime. Here g plus represent the Green's function corresponding to residue at q equal to plus k, and is corresponding to q equal to minus k. So g plus r comma r prime, that would be equal to what would be the result? That would be 1 by 4 pi square I times modulus of r minus r prime. Then the integral result. What is the integral result? 2 pi I times residue, which is minus e raised to ik modulus of r minus r prime divided by modulus of r minus r prime. Oh, sorry, divided by 2. That's it. There is no r minus r prime over here. Okay, so we can simplify it. Certain things would cancel. I would cancel. 1 pi would cancel. So finally, the result would be minus 1 by 4 pi e raised to ik modulus of r minus r prime divided by modulus of r minus r prime. So this is g plus. Now similarly, what would be g minus? So g minus is a Green's function corresponding to residue at q equal to minus k. Okay, so this is residue at q equal to plus k. So similarly, what would be g minus? So g minus r comma r prime. So that will take the form minus 1 upon 4 pi e raised to minus ik modulus of r minus r prime divided by modulus of r minus r prime. Okay, so if you look at both G plus and G minus, so both G plus and G minus takes the form of spherical wave, and that is okay because the scattering wave must be a spherical wave. Okay, but there are other issues also here. If you look at G plus, G plus is e raised to plus ik modulus of r minus r prime by modulus of divided by modulus of r minus r prime. So that means G plus is an outgoing wave, or G plus corresponding to an outgoing wave, because G plus related to e raised to ik modulus of r minus r prime divided by modulus of r minus r prime. So G plus corresponding to an outgoing wave, whereas G minus correspond to incoming wave. Okay, however, in case of scattering problem, we are interested in outgoing scattered wave. There may not be any incoming scattered wave. Okay, so therefore, in scattering problem, we can discard the Green's function corresponding to incoming wave. Okay, so in scattering problem, we can discard the Green's function corresponding to incoming spherical wave. Okay, so then what would be the total Green's function? So total Green's function is only G plus. So therefore, G of r comma r prime is simply only G plus of r comma r prime. And what is that? And that is simply equal to minus 1 upon 4 pi e raised to ik modulus of r minus r prime divided by modulus of r minus r prime. Okay, we have discarded the G minus term in the total Green's function. So then finally we will get we have got the expression for the scattering wave. So therefore, the scattering wave function, that would be 2 mu upon h bar square integral G of r comma r prime v r prime psi r prime dq bar prime. That is equal to 2 mu upon h bar square, then minus 1 by 4 pi integral. Green's function is e raised to ik modulus of r minus r prime divided by modulus of r minus r prime, then v at r prime psi at r prime dq bar. Okay, we can simplify it if you want. So finally, the scattering wave function is minus mu upon minus mu upon 2 pi h bar square minus mu upon 2 pi h bar square integral e raised to ik modulus of r minus r prime divided by modulus of r minus r prime v at r prime psi at r prime dq bar prime. Okay, so again we have not got the entire solution for the scattering wave function, but we have made certain advancement in towards our solution, because now we have got the expression for the Green's function. So this is our Green's function. Okay, so our next task is we can simplify this up to a certain amount. Okay, and after the simplification we'll go towards the approximation method. Okay, so for the time being, better we can stop it here. So in the next class, we'll discuss how to simplify this expression. So there are ways to simplify it, and we'll get some easy expression for the scattering wave function, and thereby we can find the expression for the scattering amplitude. Okay. Okay. So for the time being, we can stop it here. So we'll see in the next class for in order to make the simplification for this expression. So thank you everyone.